All right, so what effect does this common factor have on the graph of the function? Back in one of the earlier examples, we had an x minus 1 squared on the top, and we had an x minus 1 and an x minus 8 on the bottom. So we had that common factor of x minus 1, which meant we didn't have an x-intercept in that function, but it certainly looked like it. What happens is, in those cases, that common factor gives rise to what's known as a hole in the graph of the function. So if we start off with, again, a rational function, okay, nothing, same copy-pasted definition we had 3 or 4 times earlier. If both a numerator and denominator have a common factor, then f will have a hole wherever that factor is 0. So just real quick, if I had, f of x equals, and I factor it down, and I have x minus 4 times x plus 7 on the top, and I have x minus 4 and x minus 2 on the bottom, then we're going to have a hole at x equals 4, since that's the common factor. All right. Now, to say all of this is, if that common factor is px minus q, so in other words, like 2x minus 7 or something like that, then f will have a hole at positive 7 over 2. So in other words, just set that factor equal to 0, solve it, and that will give you the x coordinate of that hole. To determine the y coordinate of the hole, we're going to plug that value into the reduced version. So if I cancel off the 4 here, now when I plug 4 in, I get 4 plus 7 is 11, over 4 minus 2 is 2. That would give me the coordinates of the hole. So I'd go to my graph, and I'd put a hole at that point. And the graph would more than likely come in one side, leave the other, leaving us a hole. So find all the holes of this function. So in this case here, we're going to go ahead and take that function, f of x equals, factor the top, so it's x minus 7 over x plus 1. Common factor on the bottom is 3, and I get an x plus 1. So we have a hole at x equals negative 1. If I cancel that is, as long as x is not negative 1, then this function and this function are going to be identical. The only difference is this. Where this function would have a hole, this function is going to be filled in. So if I plug negative 1 in here, negative 1 minus 7 is negative 8 over 3. This function would have a filled in circle. This function would have a hole. All right, so let's take a look at a couple of examples. One, we're just going to look at find the features. The next, we'll find the features, and then we'll graph it. And then we'll take a look. I'm going to do a 4th video of just the application problems at the end of this. So determine each feature of the given graph. So first thing I want to do is I want to start off with, and the Delta Math problems don't ask you for it, but I do think it's important we look and we say, what's the domain? So we're going to start with our work by factoring these two polynomials, looking for common factors, and trying to do all of that analysis. So here we go. Up top, we have a common factor of negative 3. It leaves me x squared plus 6x plus 5, which factors 2x plus 5 and x plus 1. The denominator, no common factor. So we're going to have a 2x and a 1x, and that's going to be a plus 5 and a minus 1. So you can see we do have a common factor. So I can reduce it as long as I understand that this function is different at negative 5. All right, so the domain, all we do is from the very beginning of the problem, look at the denominator, find out when it's going to be 0. So this factor would be 0 at 1/2. This factor would be 0 at negative 5. So my domain is all real numbers except 1/2 and negative 5. I didn't call that part A because delta math doesn't ask you for it. So the first thing delta math asks you for is the horizontal asymptote. So to do this, I'm going to go ahead and redistribute this -3 just so we have the expanded version of this. So now we look and we compare for horizontal asymptotes, we compare degrees. The degrees are the same here, so -3/2. So y equals -3/2 is my horizontal asymptote. We have a vertical asymptote wherever this reduced form has a denominator that's 0, which happens at x equals 1/2. We have an x-intercept wherever the numerator is 0, but the denominator is not 0. So let's take a look at this numerator, -3x minus 3, set it equal to 0, which happens at -1. And since that value does not make the denominator 0, we have an x-intercept of -1, 0. Y-intercept, probably the easiest part of this entire problem. Just go right back to the very beginning, plug in 0, and all 4 of these terms would disappear, giving me -15 over -5, which is 3. So we have a y-intercept of 0, 3. Last is where's a hole? Well, again, I go back to the pre-reduced version. I say wherever we have a common factor, that's 0 of that factor is where we have a hole. So I have a hole at x equals -5. I plug -5 into this reduced version to figure out what the y coordinate of that hole would be. So -3 times -5 is 15, minus 3 is 12. 2 times -5 is -10, minus 1 is -11. Right. And that's all that we're going to have to do. From there, we can plug the information in and we can talk about the graphs of the rational function. So number 9, I already graphed it here. And this is what you're going to see when you do it in Delta Math. But I'm going to show you that as we find these features, we'll put them on the graph so you can see exactly what's going on. All right, so first thing here, this is already reduced. It's already factored. I mean, it doesn't break down anymore. So we can jump right into this and talk domain. All real numbers. Except x equals -7/2. Horizontal asymptote, it's already reduced. The degrees are the same. So my horizontal asymptote will be at x equals, or y equals, sorry, 1/2. So I come over to my graph and I draw a horizontal line at 1/2, and that's my horizontal asymptote. B, vertical asymptote, wherever the denominator is 0 in this reduced version, which is x equals -7/2. Now, it's no coincidence that the domain and the vertical asymptote and the hole they're connected, and you'll see as you work through a few of the problems how that works out. All right, so the vertical asymptote, I go -3.5, and I draw a vertical dotted line coming down. All right, C, x-intercept, wherever the numerator is 0, which happens at 3, as long as the denominator is not 0, which it's not. So go to 3, 0, put your x-intercept in. Y-intercept, plug 0 in for x, we just get -3/7. Now this is what it says up here. It says on Delta Math, it talks about like if it's not an integer, then just get as close as you can. So -3/7, I put in between. It's about half, -1/2. So I put that value in. and whole, there's none because there's no common factor in the numerator and denominator. So the question then is, how do I get my graph? Okay. Well, if we take a look, I need to have my graph go through the y-intercept and go through the x-intercept. And it needs to approach this horizontal asymptote. So you're really kind of limited to this shape right here. Then as I travel left, it has to approach. So it could somehow go up, it could go down. So how do we know? Well, here's the deal. If it went up, it would have to cross the x-axis again, but it doesn't. It would have to have another x-intercept, and we know there is not. So therefore, it has to turn and go down and ride along that vertical asymptote. Over here to the left, well, there's really, again, there's two choices for what this graph could look like. Approach the horizontal asymptote from the top and go up, or approach it from the bottom and go down. But if it did that, then in order to approach this horizontal asymptote of y equals 1/2, somewhere out here, it would have to cross the x-axis again. And it doesn't. So therefore, the graph has to be that top piece. Here's the other thing. If you get stuck and you're not sure exactly what it looks like, then take a second and plug in something like -6. -6 minus 3 is -9. 2 times -6 is -12. Plus 7 is -5. -9 over -5 is 1.8. So -6, 1.8. And if you plot a point or 2 or 3 or something like that, you very quickly get the shape of the graph. All right, so those are all the examples that Delta Math will have you do, so you should be all set to do that. There are 2 other examples that talk like some real life applications of rational functions, which I'll show you in the next video.